In the last class, I had talked of grinding, both wet and dry ball milling, uh, to crush ceramic powders to a very fine size. Before I go further on the topic, proceed with more finer details. One of the most common areas of dry ground grinding is, say, pulverization of coal. In thermal power plants, coal is brought in chunks. Some of them are as large as 2 centimeters. Some of them are finer. In the coal-fired power plant, they push in very fine coals. So what they do over there is the coal which is as received, which has got sizes varying from 2 centimeter to 1 millimeter. This is first taken to a crusher, which is normally a hammer mill, where the powder sizes are decreased to, say, 100 to 75 micrometers. I talked of hammer mill earlier, and this powdered coal is fed to the furnace, which heats the steam by air. This has been a standard process for a very, very long time. This is nothing new. Similarly, in cement industry, where they use a variety of materials. Here in the coal, in the power plants, I have talked of only coal. But in the cement industry, where they use various materials like limestone, clay, and quite a few other things, they have to be mixed in a proper ratio. So that you get to somewhere near where the cement concentration is. So today what happens is, in the cement industry, they have crushers for limestone, they have crushers for clay, they have crushers, if required, for alumina, and maybe more. All of them are hammer mill. The powders are crushed here is a fundamental thing. While in the coal, what is happening? This powdered coal is being fed to the furnace where it burns up. But in cement industry, the limestone, the clay, the alumina, and if any other additives, they have to be mixed in a proper ratio. So here in cement industry, one more factor comes in. These crushed powders are directly not fed into for calcining. First of all, these crushed powders each of them, clay, limestone, alumina, silica. First, they are classified into various size fractions. You have to realize silica is very hard. So, chances are, even though we are using the same mill, powder sizes of the silica grains may be larger. Alumina is obtained from bauxite, that is much more softer. Limestone is soft, clay can be hard or soft depending on the source. So, here what we have to do is take similar sized powders of each, so that if I schematically draw I will have a uniform mixture of say lime, depending on the ratio of lime I want. I will have a reasonably uniform mixture of alumina, a reasonably good physically homogeneous mixture of silica, and if I am using clay, a clay. Rather than, this is what we need. What we do not need, what we always try to avoid are this sort of a inhomogeneous distribution. The reason is very simple. If I take a two binary system, let me say I want AO to react with BO to give me AbO2. Does not matter what metal ion A is, what metal ion B is. Let us assume two distributions. This is an idealized one, I admit, but this is the, I am drawing it in an idealized fashion to explain the whole geometry. Let us say this is AO and it is surrounded by BO. They are randomly distributed BO, they are randomly distributed AOs, now let us assume that, or let us take the case of say MgO plus Al2O3 to give you MgAl2O4. Let us assume AO is MgO, BO is Al2O3. Crystal structure of MgO is oxygen atom at corners, face centers, and magnesium ions at tetrahedral sites. So, in the MgO lattice all tetrahedral sites are filled. For Al2O3, the crystal structure is oxygen at corners and face centers, aluminium ions occupy 2/3 of octahedral sites. For the reaction MgO Al2O3, for simplicity's sake, let us presume that it is MgO, Mg ions diffuse into Al2O3. Why? As the tetrahedral sites in the alumina lattice are vacant, the size of the magnesium ion is just correct to fit in the tetrahedral site. So, if I come back to this diagram, what would I have see if I look at say MgO? The Al2O3, as you can see, are around it. These are the Al2O3. So, the MgO will start diffusing into the Al2O3. As I had presumed that it is the magnesia which diffuses into the alumina, which is technically correct. So, in this case, what I would land up with is, after some time, MgO would have diffused into the Al2O3, with more time, more MgO diffuses in. So, what we have now is the Al2O3 grain whose first few molecular layers have been converted to MgAl2O4. Now, this poses two problems. One, this MgAl2O4 has been formed due to a molecular reaction. Hence, this layer is very dense, which prevents or slows down MgO diffusion. This is a major problem in ceramic processing, especially because we are still working with materials which binary systems where two materials combine to give you a reaction like MgAl2O4. In the laboratory, what we can do is we can take this powder, crush it and heat it, so that now more open surfaces are available. But this is not possible in the ceramic industry, because it is a line process. You have the powders thrown into the calciner and the reaction has to be complete. So, the first thing is over here in this, for example, in the cement industry, where I talked of these powders, we need here a reasonably homogeneous mix. This is paramount. Second, fine enough size for diffusion to complete. These are two major issues which have to be addressed in dry grinding. The powders have to be homogeneous. Remember, I have got 4 different materials: silica, very hard; alumina, I can take from bauxite ore, which is less harder than silica; limestone is softer, and clay is somewhere in between. So, our goal is basically to have a reasonably homogeneous mix along with fine enough powders. So, when we are in this cement industry, let me come back to this and then take over. Each of these have to be classified into various size fractions. Why? So that uniform and fine size powders can be made to react. So, what is done in a cement industry is sand, alumina, though we can start from bauxite, clay, limestone. Each of these are crushed in, say, hammer mill. If you remember, the hammer mill can give you really fine powders down somewhere down to about 50 to 25 microns. Then each of these are what are called sized into different fractions. We can have over here, what we can have is, say, particle sizes, this is a particle size and this is a size fraction. It is different, so that we can choose whether we want this particular size or this particular size of powders. This is done, all of this is done by air classification. The air classification system has been there for long enough. It has been there for a long time for different industries. And over there what is done is, we have got a system which is drawn very crudely. I have shown this in detail earlier. The powder is fed in and there is a high velocity air that is in circulation. There are the finer powders, they circulate in the outer periphery, the coarser powder in the inner periphery. These finer powders are taken out. The coarser powders can be returned back to over here for grinding the finer powders. There are various types of air classification systems which are available, and hence one can look them up on the net. So basically they are air classified, then size fractions are selected. Now all you have to remember here, from the hammer mill all the powder is being fed into the air classification system by high velocity air, and this high velocity air is being fed into the air classification system, and the powder which is collected from here is again picked up by air in a closed circuit. So, these size fractions are selected and then they are again mixed in desired ratio and fed to the calciner. The improvement in cement technology that is happening is because couple of things. One, these air classification equipments size fractions are being chosen very properly. The whole thing is an assembly line fashion, and as a result we can here from size, after doing the size fractions, we can vary the amount of limestone, clay, alumina, sand depending on a requirement, make sure they mix, and in the calciner we do not have big pebbles to calcine, we have very fine powders which we calcine. The best cements of today that you see are very, very fine powders, and that is where all these dry grinding processes come in very handy. However, this is also applied for many industrial products manufactured, like say the high tension insulator which you see, where they mix silica, clay, feldspar and then get the powders to fabricate the high tension insulators. A lot of plenty of the commercial piezoelectric crystals, say used in where you use the kitchen igniter, the igniter with which you start your flame, is also made by this process, where you need to mix 3 different compounds or 4 different compounds to get the proper composition. However, when we are talking of very high end products where purity is a factor, for example, if you ever bother to open up a waste a spoiled kitchen lighter, you will see that the central crystal, which is basically lead zircon titanate, is a black one. It is black simply because there are contaminants like iron oxide and all of it. It is good enough for a kitchen lighter, but if you had to use it for say defense or space purpose, it will be totally unusable, because in such cases, whether in defense, space, medicine, you require ultra pure lead zircon titanate crystals. There you cannot afford to have the impurities which you see in the piezoelectric crystal which is available, which is used in the kitchen lighter. So, in these cases where we require very high end products, let me take the case of a capacitor which is used in space, which is based on barium titanate. If I am looking at the dielectric constant versus temperature, the so called very high dielectric constant is there only at this Curie temperature, which is 127 degrees centigrade. Now, no device will occur in this place. What we really need is a reasonably flat response across a temperature from near 0 K, because you are in space, to a temperature somewhere near 800 K. So, what is done is additives are added so that they have got this Curie temperature which varies depending on the type of additive. We use various types of additives: calcium, strontium, zirconium, and a huge lot more. So, here, and the amounts are very small. In some cases, we have amounts as small as 1% to 10%. So, here we will have to mix barium carbonate, titanium dioxide, calcium oxide, strontium oxide, zirconium oxide, and the list does not end here because a lot of it is in the secret zone. So, each of these have to mix in the desired ratio, so that the final product can give us a capacitor which has got a reasonably linear response, so that it is usable in space. Presence of impurities in this system will simply destroy the capacitance effect. So, here we need ultra pure products. If we had tried to use any of this process for synthesizing the powder over here, we would have a useless powder. So, here for this sort of a capacitor which I am talking of, which has got a very high dielectric constant, which is used in space, which has got a constant dielectric constant over a wide range of temperature, for mixing so many products, the only viable process that we have is a ball mill. Now, in a ball mill, I had talked of both dry and wet. You see, the problem here is, if I try to wet ball mill barium carbonate, calcium oxide or calcium carbonate, strontium oxide or strontium carbonate, all of them would react with water to give you the corresponding metal hydroxides. This is a major problem. So, wet ball milling in this case is ruled out. All of these have to be dry ball milled. Otherwise, they would all hydrolyze, give you different amounts of hydroxides, and then batch calculations becomes very difficult. I told you the problems of dry ball milling. What happens is, as we try dry ball mill, if this is the solid ball, what we would see is a coating of the powder develop over here, and finally the milling operation stops. So, I had said we use milling aid. One of the most common milling aids is stearic acid. Stearic acid is a main component in what you use as soap. So, what this stearic acid does is, the stearic acid coats the powder, as stearic acid is slippery, agglomeration does not occur. Agglomeration does not occur. So, in dry ball milling, when we have to resort to it, because wet ball milling will give us other products, we have to use these grinding aids. And these grinding aids should be such that they burn off cleanly. What do I mean by the word cleanly? All of these organic compounds have got carbon. So, if it is heated too fast, what will happen? A large part of the carbon will be converted to carbon dioxide, true, but some of the carbon will remain and they will create problems in later sintering steps. So, these grinding aids have to be chosen very, very carefully for dry ball milling. Now, if I am talking of milling efficiency, this is just an indicative thing to give you some idea, is that if this is the particle size after milling in a log scale, and the y axis I present the slice fractions. Let us presume for a particular system we have dry ball milled it for say 24 hours. If I use proper sintering grinding aid, this is say 24 hours. Now, what would happen if I grind it for 48 hours? Maybe I would get something like this for 48 hours. What would happen if I keep on grinding it for 72 hours? This is where further grinding efficiency is not obtained. You can see the size reduction is not much. The amount of energy spent far outweighs the benefit of size reduction. So, in dry ball milling, due to various factors, we have a limit below which we cannot reduce the particle size. In wet ball milling, if I am considering wet ball milling, I may have powder sizes down to here. Now, the first change you see this here, look at the size range at half height, this is wide, but over here it is much narrow. So, in wet ball milling, one of the things that we can achieve is narrower size distribution with particle size being finer than with dry ball mill. However, over here getting finer powder sizes over here is a problem, because in wet ball milling, the slurry which of the solvent and the powder is there between the balls, and hence in wet ball milling, erosion or corrosion of the walls is a major problem, and contamination can occur if we try to use wet ball milling to force to go down to lower and lower sizes. In many cases, what are used are for wet ball milling stainless steel container with rubber lining, so that the contamination from the walls do not happen. If the rubber may erode, but then the rubber can be burnt off during subsequent calcination operation. Yet the other problem with wet ball milling is the particles have to remain suspended in solution. If the solvent is such that the particles precipitate, then ball milling will not occur during wet ball milling. Frequently surfactants, like say the common soap you use for washing your clothes, that is a surfactant. Such surfactants are added during wet ball milling to keep the powders afloat, so that they stay suspended and are ground down. Here the role of the solvent has a major effect. In wet ball milling, because the solvent is compatible with the particle that you are crushing, frequently the solvent, which is water nowadays, tends to force agglomeration at finer sizes. So, if you take alumina and use water as the solvent or the medium on which to suspend, the alumina grains will crush, water will get between the crushed grains forming hydrogen bonds, leading to agglomeration. To prevent this, surfactants are added, but the major problem says as the particle size gets finer and finer down to say 2 or 3 microns, the surface tension effect of the water which coalesces the alumina particles becomes very high, and the grinding essentially stops. One of the ways in which very fine particle sizes down to submicron level are obtained are attrition ball mills, where we have in a schematic drawing a tank with an impeller which rotates at say 1 to 10 hertz per second. This is filled with balls and the ceramic powder plus the liquid media, which today is essentially water. Here what happens is, as this rotates, these balls also start rotating. Here the scenario develops is the balls are rotating, each of the balls are rotating as the impeller is moving. The impeller is rotating, forcing the balls to rotate. The diameter of the ball is somewhere from 5 millimeter to 1 centimeter or 10 millimeter. The powders and the slurry which are over here, they undergo far more intense impact and impact between the powders themselves. Let me expand this diagram more. These balls are rotating as the impeller is rotating somewhere between 1 to 10 hertz. The ceramic slurry which is over here, as in the ball mill, is now also rotating. The only difference here is that as these balls are rotating, in this particular area there is a huge cyclone which is generated. You remember, these are the balls, this is a very small area, and in this area the liquid is moving at a really high angular velocity. At this velocity, the ceramic particles impact with each other. In a ball mill, I am using rotation speeds of about 1000 RPM. In this sort of this is what we call is planetary attrition ball mill. The rotation speed is hardly 6 RPM, 60 RPM. So here this impeller is rotating at 6 RPM, 10 RPM. The balls are rotating at a much more slower speed than 100 RPM, but because they are smaller and very compact, in this particular area we have very high angular velocities, causing the ceramic particles to impact with each other and lead to size reduction. Along with the very fact that now because here it is ceramic particle to ceramic particle impact, contamination is minimal. This is one of the major advantages of planetary attrition ball mill. That is the because here it is a particle-particle impact which is crushing the powder, rather than the ball impact in ball mills. Contamination is minimal. There is no scratching of the walls of the vessel by the balls. Hence, the wall contamination due to erosion of the wall is also minimal. The particle size distribution here, if I use this diagram, this one was for wet ball milling. these three were for dry ball milling. If on the same scale I draw for attrition ball mill, means this is down to 0.1 micron and this is 0.001 micron. With a planetary ball mill, particle sizes in this range are routine. That is, submicron particle sizes are routinely available with attrition ball mill. And the advantage of having narrow particle size distribution means we can take the powder as is received. Yes, there are many issues, lots of issues over here. Like say if I was grinding, if I was attrition ball milling alumina, I would have in that case, if I am alumina attrition ball mill, aqueous media, I could get 20 nanometer powders, but then it were mixed of Al2O3 plus hydroxides of alumina. Because as a powder size reduction has occurred, the surface, this is formed due to reaction with water. And hence, with attrition ball milling of alumina, we can get particle sizes down to 20 nanometers. I routinely get them, but I am hamstrung with the fact that it is a mixture. So, this has to be processed again, means one of the easiest thing is to heat it so that I get back alumina all over again. But then the problem that happens is agglomeration happens during heating. So, you see in all this process of ball milling, there are advantages, there are disadvantages. One has to basically balance what is the ultimate need. You see, in this particular case, where I ball milled, attrition ball milled alumina, due to the very fact that I used aqueous media, one more unit operation is being added, which is heating. That is something of a major cost, capital cost in terms of industry. So, unless the industry wants a very highly value added alumina product, it would never take recourse to this method. Unless it is such a valuable item that the addition of this heating, even if it adds to the product cost, does not matter. In such cases, they will go in for attrition ball milling. However, as an aside, I would say attrition ball milling is a major source of getting fine powders by the healthcare industry. For example, all those creams that you see which say that the clay, nano clay gets into your body, causes swelling, that clay is obtained by attrition ball milling. Many of the colorants which are used for facial makeups or for lipsticks are obtained by attrition ball milling. In such cases, they use it because all they need are the powders. They do not need to subsequently process it into any shape. They will use the powders and that is the end of it. But the main problem comes in when powders have to be consolidated. You see, let me take the simple case of this. I have, because this is a routine major problem in alumina processing, and every alumina industry faces it, is if you have got a mixture of alumina and hydroxides of alumina, I am heating it. I said agglomeration occurs during heating, even though the maximum temperature I have employed here is 700 degrees centigrade. Why does it happen? Because this agglomeration is undesirable. The reason that happens is the AlOH3 thrice, which is aluminum hydroxide, when it decomposes, it generates ultrafine 1 nanometer alumina powders or less, and these have such a high surface free energy that they self sinter or self agglomerate. This is a major problem, but the advantage of the ceramics industry is the technology is so difficult that they turn this disadvantage into an advantage. So, in the ceramic industry what they would do is they would take this powder, do a careful chemical analysis of how much alumina is there as Al2O3 and how much alumina is there as hydroxide, use it as such and then do reactive sintering. With very powerful effects. Again, to recap, they would take this alumina powder which has got both alumina and hydroxides of alumina, they would shape it into whatever size and fire. Here the firing would be at 1100 1200 degrees centigrade. During this firing process, the aluminum hydroxide would decompose, as I had said earlier, giving you almost nanometer sized alumina powder. These powders would be so high in surface energy that sintering would start at a much lower temperature than it would have had if they had taken micron sized alumina. So, frequently in alumina industry you will see that alumina has been wet milled, there is partial conversion to aluminum hydroxide, yet that same powder is taken, calcined at 700 degrees centigrade to convert some of it to aluminum oxide. That aluminum oxide and aluminum hydroxide powder mix is shaped and fired, and that is where this reactive sintering is used very powerfully. I will stop here. In the next class, I shall pick up chemical synthesis of ceramic powders. If you look into the literature, there is no end to ways people are innovating ball milling operations to improve productivity, because they need better quality materials. If I am doing wet chemical synthesis, as I said, one of the biggest problems is I will get some hydroxides, and that has to be calcined adding to unit operations. And nobody does chemical synthesis of powders unless it is a very, very high value added item. But ceramists have worked around the problem, and that is what I shall pick up from the next class.